Hello all. Today we're going to be looking at some more applications of series. And so when we actually take a look at something like this, where we're adding together, and you can see that there's kind of a pattern here, we actually call this a power series because it is depending on kind of what our x value is. And so it is geometric because there's a multiplier of 3x each time. So it is geometric, like it's talking about right here. But it really does depend on those x values. So if I do an x value of 2, and I actually look at my common ratio, it's going to be bigger than 1, so my series diverges. But if I look at an x value of 1/4, then my common ratio ends up becoming 3 times 1/4 or 3/4, then my series converges. So there's some values that my series will converge for and some values that my series will diverge for. And the way that we can kind of figure that out is by taking that 3x and saying, hey, I need that to be less than 1. Oh, so if I actually solve that out, x has to be between -1/3 and 1/3 for our series to converge. And we actually call this our interval of convergence, for a power series. And just like we did that with a geometric series, we can also do that kind of using our ratio test. So we can look at, oh, well, what is happening as our terms go on? So if we look at our ratio test of n, or x to the n divided by n factorial, then my limit is actually approaching 0. So in this case, my x value, as long as my x value isn't as large as that n value, then we'll be good. But in this case down here, it's actually very much dependent on what my x value is for it to converge. So I can take that absolute value of x minus 1 divided by 3, and I know that that has to be less than 1 because, geometrically my ratio has to be less than 1 as I'm going on. So this is a slightly different interval of convergence, And our true question here is, do I actually include -2 and 4 in my interval? And so I'm actually going to use those as testing points. If I plug in -2, that is convergent by the alternating series test, but if I plug in 4, it is actually divergent because it's a harmonic series. So this is what my interval of convergence actually looks like right there. My interval of convergence is from -2 to 4. It's centered around x equals 1, and it has a radius of 3. Okay, now that we've kind of looked at some examples, this should start to actually kind of make sense right here. So I have a power series definition, and we just looked at some power series in that example from right before. So like our x to the n over n factorial, that's a power series. And we have certain numbers that they can diverge or converge for depending on what our x value is. So that's what these examples actually look like. And maybe it just converges for one value. Maybe it converges for all of my x values. Maybe it only converges when x is a particular value, which we would call our interval of convergence. And this example we actually just talked about, but that is okay. I will actually take a look at, again, using kind of the ratio test here because we're looking at subsequent values as we go further and further out, as that approaches infinity. What is actually happening to our ratios or to our, it's not a constant ratio because it's changing over time, but what is actually happening. So if I take a look at my ratio test, I'll have x to the n plus 1 over n plus 1 factorial all over just my term itself. And then I'm going to multiply by the reciprocal on the denominator. And I'm going to peel apart just like when we were doing our ratio test. I'm going to kind of peel those apart. So I'll have x to the n times x all over, and then I can rewrite my n plus 1 factorial as n plus 1 times n minus 1, but I'll just write this as n factorial because I want these things to cancel out here, and then my x to the n cancels out there, and I'm just left over with x, well, my limit of x over n plus 1. So in this case, as my n gets bigger and bigger, this is going to be 0, and this converges everywhere. My interval of convergence is that this converges for all x values. Hence, my radius is infinite. Okay, I want to look at this next example here. So again, I'm going to use my ratio test, and I'm actually going to peel apart that factorial and the x to the n plus 1 to be x to the n times x. I have some values that cancel out here, and I'm just left over with my limit as x is approaching infinity of n plus 1 times x, which, because my n is getting bigger and it's not in my denominator, this is actually going to be infinite, and the only thing that would cause it not to be infinite is if x is equal to 0. So this series diverges for all x values that are not equal to 0. And since this is centered at x equals 0, that's the only value that this will actually converge for, our radius of convergence is 0 and our r value is 0. I went ahead and wrote all of that down, and I want to look at our next example. Our next example looks a little bit more funky, but we can actually kind of see that our x value is not going to be centered around 0. This top part is telling us that it's probably going to be centered around 2. I'm going to go ahead and use my ratio test here. To save on a little bit of time, I have my n plus 1th term up here, and I know I'd be dividing by this same thing down here, but instead I'm actually going to multiply by its reciprocal. Some weird stuff happening here, so I'm just going to try my normal thing, which is like peeling apart the n plus 1 from my x minus 2. So I'll have x minus 2 raised to the n power times x minus 2, and I'm going to do the same thing with this 3 to the n plus 1 down there as well. So I have done a bad job of like actually talking about the absolute value bars being here, but since I didn't have a negative 1 raised to the anything power, it didn't really matter. I am going to cancel some things out here, so let's just rewrite what we have. So to make this really, really clear, I'm going to throw my n plus 1 and my n plus 2 that it's on the numerator and denominator together, and then we're really thinking about the x minus 2, this term right here, and my 3. Those are kind of like my coefficients that are out in front. My limit is just as n is approaching infinity, so as this n plus 1 over n plus 2 gets bigger and bigger, it's going to approach the horizontal asymptote of 1. So really what I'm looking for is this chunk right here, my x minus 2 divided by 3. I'm really looking for that chunk to be less than 1, because if it's less than 1, then I know that this will converge. I'm going to go ahead and rewrite this as x minus 2 over 3. It could be less than 1, but it could also be greater than negative 1, because I could have all of the values in here be something negative, like end up being negative 1/2, and it would still actually converge because the absolute value of it would be less than 1. Okay, now that I have this equation, I'm going to multiply by 3 and add 2. So my interval of convergence here is really going to be from negative 1 to 5. We do need to check the endpoints. So I'm going to go ahead and plug in negative 1 and 5 to my x value up here and see if I can determine what's happening. So when I plug in negative 1 for my x, I will actually get the series negative 3 raised to the n over n plus 1 and then 3 to the n. And I can actually separate this negative from the 3, so I can actually write it as a negative 1 to the n power, and then now these values will cancel out and we'll see something that we should be able to recognize here as a series that for sure is going to converge, because it, even though it's harmonic, it's an alternating harmonic, so that's going to converge to something. So I can include negative 1 as an endpoint because I know that this converges. Okay, on the other hand, if I actually plug in 5, I'll get something that I will also recognize as just a harmonic. So I'll have 1 over n plus 1. That is harmonic and it diverges, so it's going to go to infinity, so I'm not going to have it equal to 5. Thus, my interval of convergence is from negative 1 to 5. And my radius of convergence, since this is centered around 2 up here, my radius of convergence is 3. I'm going 3 away from 2 above and below. So kind of a cool thing here. So recall, remember, this is geometric. We're dealing with like all geometric, and we're saying, hey, we're using the ratio test. We're using what we know about geometric series to see if this converges. So this Desmos graph actually gives us a really cool visual on that. So basically this is my geometric term that I have right here, and my n value is like I'm going out towards infinity. I'm going to go all the way out to 1,000 if I possibly can. So what's going to happen here is right around the, well, I'm actually doing this pretty fast, but you can see that the further I go out, so this is just a finite series from n equals 0 to now 500, that it's actually becoming closer and closer, and I was doing it too fast, it's coming closer and closer to what we know that it actually converges to, which is 1 over x minus, or 1 over 1 minus x. So kind of a cool visual on that. Okay, so using that we know that this is true, I can actually rewrite functions as power series. So in this case, if I rewrite this as 1 over 1, and then I have a minus in my equation up here, so I'm going to do minus negative x to the third. Now I can rewrite this. As a function, as a series here, where my x value, so my x value that is highlighted right there, is actually going to be negative x to the third. So I don't know about you, but that's actually really cool. Like we took something, a function that we maybe know of, but we rewrote it as infinite sum of terms. So if I start plugging values in here, I would get like 1 minus x to the third plus x to the sixth minus x to the ninth plus x to the 12th. And you can kind of see that pattern there. So the further I go out, the more it's going to actually become this equation. So any finite sum that I have, but if I look at my infinite sum of this, it will actually be equivalent to what I have here. Now this kind of begs a question like, what is our interval of convergence going to be? And so I want us to remember that for a geometric series, so if I just have something that is like a to the rn, where r is my ratio, my r value here has to be less than 1. Well, my r value is actually the same thing as this negative x to the third. So as long as negative x to the third has an absolute value that is less than 1, then I'm all good to go. And I'm actually going to try solving this out. So I took the absolute value, which ended up being positive, and I can get rid of my absolute values by putting it between negative 1 and 1. And if I solve this out, I will actually get that x is going to be, well, if I take my cubed root, it's also still going to be 1 on this side, and then cubed root of negative 1. Oh yeah, negative 1 times negative 1 times negative 1 is still negative 1. So when I take my cube roots right here, I'll still just get my same interval of convergence from negative 1 to 1. And it would be good to actually check those endpoints that we have. And actually, I think that's kind of silly too, because this is right here not actually like a less than or equal to, it's only strictly a less than. So I don't need to check these. They're just going to be strictly not including negative 1 and 1. And you can actually see why over here, if you plug it in, you'll get something that doesn't exist. Okay, we're going to look at one more way to write a function as a power series. So we're going from a function right here to something infinite, like an infinite way of representing this. So my whole goal is to try to get it like 1 over 1 minus something, and then I can plug that something into my equation. And actually, this is okay if this has an a value in it. So what I'm going to do is I'm actually going to multiply by 1/4. So on the top, I'll have x over 4. That's kind of going to be like my a value that's up here, over, and then when I distribute this 1/4 on the bottom, I'll have 1 minus, and then an x squared over 4 right here. So now I officially have my a value, and I have my r value, and I can actually write this as a geometric sequence. So there is my geometric sequence, and then since that's my r value, my x squared minus 4, that is what has to be less than 1. If I finish actually solving that out, I should get my interval of convergence to be -2 to 2. And I can also simplify this down and make it look a little nicer if I want to. And if I simplify it down and make it look a little bit nicer, I'll get x to the 2n plus 2 over 4 to the n plus 1. Okay, bye y'all. Have a great day.